Okay, okay. So hello everyone, and welcome to our first CENOS antenna design webinar. So thank you very much for being here, where you will be introduced to an overview of the software from the modeling to the solver physics and result visualization. All in a brief and introductory manner. This won't be too much in depth. This is only the first series of a series of webinars dedicated to antenna design. So you should expect more to come. And as this is the first one, today we'll just cover the basic overview of the software and its tools. But in the next ones, we will dig deeper into geometry creation, meshing, and results, and physics of various types of antennas, starting with PCB, working our way up to dipole, wire, horn, etc. Of course, if you'd like to suggest topics for future webinars, feel free to write them down in the chat. And if you have any questions, feel free to ask them. And by the way, we will also have a dedicated Q&A session at the end, so you can sort of ask any questions you'd like about the software, and we'll try to answer them. So I think you can all see my screen here. So let's jump right into it by opening up CENOS and navigating around the main interface of the antenna design platform. So here we have the software. We will go through the geometry, the physics, and the results, the results aspects of the software. So let's start with the geometry editor, which is this one, or Freecad. And let's save the case before proceeding. So let's name this, for example, webinar, or you can name it anything you'd like. So let's wait for this to load up. Okay, so this is a brief overview of the Freecad interface. Now we won't get into too much detail for every little feature that the software has to offer, but we've got a couple of panels and sections, as you can see here. And let's begin with the available shapes, which are quite common. For example, so Freecad is a versatile geometry editor, essentially, toolset that allows you to add many sorts of shapes. For example, let's create a cube solid. We can create a torus, a cone solid, and many more. There's a lot of shapes to choose from, and you can edit your own, build your own shapes, custom geometries, things like that. Now, in the top right corner, we have a couple of options related to geometry modification. For example, we can extrude selected sketches. We can revolve a particular shape. We can mirror an object. We can fill the selected edges of a shape, and many more. There's a lot of options here, as you can see. And this allows you to create all sorts of geometries, even if they are somewhat complex, which is common in various antennas nowadays. And this encourages high precision modeling and ultimately the most accurate results for your antenna. So you can model exactly, model your antenna exactly as you need it. Additionally, CENOS offers some RF engineering related tools for geometry modeling, such as feed network generation, PCB flattening tools, and others, which enable rapid prototyping of a variety of antenna models, of course. And in case you want to create surfaces, which are very useful for modeling patch antennas and microstrip networks and designs in general, you can also use the sketcher tool integrated into Freecad, which is over here. So here we can either select sketcher or just go here directly. And here you can see that the layout has changed here. So let's click on create a new sketch and click OK. As you can see, the view automatically changes to a two-dimensional orientation, whereas before it was a 3D view. Let's create a rectangle, for example. So we can select here a rectangle, choose 2 points, and there you can see the rectangle has been created. And if you hover over the edges or ends of the square, you can see the color changing as you highlight it. And yeah, once we said that, we can just press escape, and there you go. Now it's like with the rest of the other shapes, and we can move around the model, hover over various objects. Now, one of the key needs of an antenna designer is to build a geometric model and be able to rapidly adjust the parameters of their design without much hassle. Now, Freecad allows you to enter your parameters by going into CENOS parameter in the panel on the left. Here it says CENOS. And for example, let's say I'm designing a microstrip patch antenna and I wish to easily adjust the width and length of the patch element. I will simply enter length and set this, for example, 30 millimeters. This is just a random value. We can set, for example, width to 25 millimeters. And you can see that it automatically it gets entered. It's like an Excel spreadsheet sort of thing. It's a table basically. And I've simply entered the width and length of some parameters, and I've assigned the corresponding value. And of course, if you have more shapes, for example, the thickness of a wire, you could also add an extra parameter. So for example, thickness, let's say I want this to be 5 millimeters, for example. So I've added 3 parameters here. And now that we've got some parameters, then let's try adjusting the dimensions of a shape. Let's start with a torus, for example, here. You can see the properties on the left. On the bottom left panel, we have a few parameters. And let's set, for example, radius 1 to our parameter. Let's say, obviously we could hard code this and say 5 millimeters, but if we want to quickly adjust some parameters, it's useful to load the parameters directly from the table that we've just created. So for example, if I had this parameter in multiple shapes, I could switch them very fast, and they would all update at the same time without a lot of work. So let's set the radius 1, for example, to CENOS parameters, dot, and then the name of the parameter. And you can see that as I enter the name, that it displays automatically. It finds exactly what you're looking for because it sees that it starts with THI, so it has to be thickness since I don't have any other parameter starting with this name. So I can select it and click OK. You can see here, you might have noticed that the torus just shrunk. So it automatically updates. So let's set, for example, a different value. We can set, for example, 20 millimeters. And if I go here, you can see automatically it changed. So this is very useful. And as you can see, by navigating around the model, the diameter of the torus has clearly changed, and the model has been updated automatically, essentially, which is very useful. Now, you can also import more common antenna components directly by clicking on the component library at the top left, and loading, for example, we have patch inset, SMA panel connector. For this example, let's just load the SMA edge connector. So just select this and click create. And you can see that it's added here in our model. Obviously, it is on top of another of the cone here. So it almost looks like a horn antenna, but that's just a coincidence. Of course, there are different shapes. And you can see this on the left, by the way. You can see that by selecting different objects, and if we press space, we can disable the view. Also for the cube, let's say I only want to see the connector. I can just press space on the torus, and it just disappears. So let's just re-enable this real quick again. Finally, once our model is finished, it's time to mesh it. We can directly apply mesh to, for example, the cube. So I can select the cube here. Okay, and by selecting from the list of objects, and on the left, here on the left, we select the cube, which you can see it's the cube by simply pressing enter, and it will enable and disable it, its view. And by selecting it from the list and clicking on the meshing icon at the top left, this one here, you can see it says meshing. You can see that the sections icons have changed, and are now intended for meshing rather than geometry modeling. So this is the part where you might have to be a bit careful. Now, CENOS allows you to automatically mesh this cube. Like here, I can just It's one click only, and it will create a mesh. And and depending on the model, of course, if it's a very complex geometry, very large geometry, it may take a bit more time, of course, depending on your machine, obviously. And now you can see that the cube has turned purple, and the mesh grid lines are clearly visible. This is an indicator that the object of interest has been meshed successfully. And you can see sort of the lines here going through around the cube, like little triangles. And you know, obviously, depending on the frequency of your application and things like that, if the automatic mesh appears to be coarse, you can always make it finer. CENOS allows you to do all this stuff, of course, without any problem. So this is basically Freecad. This is one out of three things that CENOS covers. So now that we've taken a brief look and understanding of the geometry editor, which, by the way, we will probably look into more detail in future webinars in the series, we can close out of this. Let's say I don't want to save it because it was just a quick example, and let's just create a new case. And because I want to guide you through the physics and results, so to give you a very brief idea of the software, to understand how you model an antenna, which we've just covered very briefly, but we covered the geometry editor, how the physics run, how the solver runs, and how the results look like, how to visualize the results, how to interpret them, the plots, the 2D, 3D plots, and everything. So let's just start with a template, for example. So let's just click on template and enter in our parameters. Let's adjust, for example, the substrate. Obviously, CENOS already gives you some dimensions here. So you don't have to, you know, if you want to do a quick test, just leave them like this and press go to physics. But we can also just zoom in, by the way. Okay. Yeah, let's set the substrate width, for example, to 80. And if you're careful here, you will see that if you pay attention that the dimensions have changed. And you can also zoom in around on this, pan around, rotate, to see that whether your model is actually, you know, what you're looking for. This is not only the case with templates, you can also do this with geometry editor. So you can finally create your mesh, send it to CENOS, and then it will display it here on this panel. So you can get a very good idea of, you know, whether your model has actually been imported correctly, whether it was, you know, maybe a wrong file or something that you've loaded. But yeah, this looks fine. Now, let's say I also want to adjust the length to 75, for example. And yeah, you can see that this is obviously there. And by the way, if you enter a very odd value or invalid value, CENOS automatically lets you know that, hey, the substrate length should be a positive number, obviously. This prevents users from accidentally entering random numbers or incorrect values or negative numbers, things like that. So let's set this to 75, an example, and the model has changed. And now once these dimensions have been optimized, and we are happy with dimensions of our model, we can proceed by clicking go to physics at the top right. And by the way, many more templates are about to be launched. So you might see only 2 now, but we will get out more templates soon. We've got 2 microstrip designs and 1 horn design. So you can look out for that. Now, once the dimensions have been optimized to some optimal dimensions of your choice, and we are happy with the dimensions, we can proceed by clicking on go to physics that we did, and we are asked about our signal excitation properties. Let's set a starting frequency, for example, 2.2 gigahertz, or let's say, because we don't want this to take too long, but okay, let's set this 2.2 gigahertz and 2.5. And let's set the step to, let's leave it to 50 megahertz. Or maybe let's set this to 2.3 so it doesn't take too long. So we've got a few tabs here. And we can proceed by setting various settings at these different tabs. For example, we can set a particular dielectric material. It lets you know that what material you've selected. So you can click select here and select your own material. We've got FR4, we've got, you know, all sorts of common dielectrics from Rogers, things like that. And if you select one, for example, RT Droid 5880. We've got the dielectric constant, which is 2.2, of course. Some of you might be familiar with this material, with this dielectric. It's a very good dielectric for antenna design, and it's used often. So we've got the magnetic permeability, the electric constant, the electric loss tangent, everything you need that you're concerned in terms of, this is not properties, mechanical properties or thermal properties, but rather electromagnetic properties. You can also create your own material, of course. You can clone, you can create a copy of this. It's just one parameter. So it's a very versatile tool that allows you to customize your antenna exactly as you need it and produce the most accurate results for your antenna. We can leave the material to air here, the vacuum sort of boundaries. And here the boundaries tab, finally we've got the boundaries tab, which allows us to set a custom impedance of our choice. For example, I could set this to 75 ohm, for example, if I was designing maybe a TV antenna, which has a different expected impedance. And more parameters related to the port of the antenna. You can see here a uniform port. We could set this to coaxial depending on our design. We can set some materials here. Let's leave this to PEC, and so on and so forth. So yeah, so this is essentially the basics. So we've created our design. So we've seen how. Okay, let's just run this, by the way, so we don't wait. Okay, yeah, so it's preparing the geometry now. It shows it here. And you can also zoom into this as well to see exactly what's going on. It tells you what your system is, what your specs are, and when it says get dB microwaves calculation, so you can see here at every frequency step once it's done. So it's using the finite element method, so it runs the simulation for its frequency, and you can see here that the results go on and more get produced. So we've seen the geometry editor. How do we create a very simple antenna, for example, or very basic model? We've seen the templates. So CENOS allows you to very quickly do your own thing. And now we're going to look at the results. So now when it says post-processing results, we should expect to see ParaView notifying us that the results are available for us to view, the 2D and 3D plots. So we will get to this. So yeah, sometimes the post-processing results can take a bit if you have a very wide frequency range or a very fine frequency step, because it has to process a lot more data points. Although we might fix this and implement another library for this to view data even faster. This is on our to-do list. So yeah, now it says computing in process and in progress, and we can expect this to finish in about a second or two.
While it is calculating, maybe we can use the time for already on the top questions. If anyone has about something that we have already discussed up until now, why not? We can go over them.
Sure. If anyone has any questions, feel free to ask ahead or ask in the end, whatever you prefer.
I would like to actually to ask. I recognize that in the geometry object, so in the Freecad, so that there is an option to add some more objects. So it's just like it is. So I just press the button add, and I can add my object there or something else.
You mean you're referring to the components library?
Well, yeah, in the Freecad. So in the Freecad.
Yeah, where I loaded, for example, an SMA connector, you mean?
Yeah. Yes.
Yeah. You can load an SMA connector. You can load some patch antennas, and you can also create your own sort of component. So you can, for example, model some N-type connector, for example, or something else, or some sort of microstrip antenna, whatever. And you can actually save this, and then you can import it from the components library. So every time, for example, let's say you you design antennas a lot which contain N-type connectors. You can, for example, model an N-type connector, save it into the component library, and then every time you open CENOS, every time you want to design a new antenna, you can just go to the component library, get the N-type connector out, and distribute it in whatever antenna you need. So that's one of the key roles of the component library indeed. Okay, I hope that makes sense. Do we have any other questions for now, or should I proceed to PowerView?
It seems there are some in chat.
Okay, let me see if I can read it. Yes, it is FEM. Is tool feasible of using lumped element in 3D simulation? Like, I guess you mean like custom resistors and capacitors and things like that. Not yet, but I don't know if it will be too difficult to implement. We haven't found an immediate use for it yet, but we should be able to support it soon. So this is definitely something we're looking to implement in the near future, along with many other features, by the way. We've got a lot of things to push out, which are quite exciting. You guys, it's a new tool for everyone. Whenever you start using a new tool, you have to get a quick feel of how it works, so you can use it easily. Jorge says the software looks very friendly. Thank you about this. Could you please plot efficiency? So we've got okay. Let me go to PowerView first and describe the results, and because some of these may be related to this. So we've got two plots here. So PowerView automatically started up. We don't have to do some weird thorough process to open it up. So we've got the PowerView window here, and we have the radiation pattern of the patch antenna. And you can see a nice pattern here. As expected, it radiates frontwards. And you can pan around and see the directivity of the antenna. On the right hand, we have the electric field in volts per meter. And you can see this is the backside, so there's not a lot of intensity here. But on the front, especially in the inset here, at the sort of feeding point, we've got a lot of many volts per meter. So you can also directly, if you rotate in one hand, in one panel, you can see the change immediately on the left. So it's very easy to visualize this, pan around and see the radiation pattern. Now, the radiation pattern is often useful to look at the 2D plots. For example, if I go here, you can see there's many 2D plots. And you can look at all sorts of patterns. Here's the pattern, for example, for the patch. And lastly, last but not least, we've got the other 2D charts tab, including the reflection coefficient, or S1 magnitude here. You can see the antenna resonates at about 2.4 gigahertz. Obviously, we picked some somewhat arbitrary parameters, so this one could get far below minus 10 dB. We also got the Vswr, or Vswr, as some pronounce it, which essentially tells us something similar to the reflection coefficient, that is how much percentage of input energy gets reflected, and how efficient the antenna is at the particular frequency. And we also got the impedance resistance. Well, first of all, we got the accepted power. You can see that 2.4 gigahertz, we get a lot of accepted power. And of course, we have the impedance. That is the complex impedance. So we've got the resistance, the reactance, everything plotted as a function of frequency, which is extremely useful, of course, for all sorts of measurements. You can also measure, of course, impedance in a vector network analyzer. So yeah, this is the basics of PowerView. Or maybe not the basics. This is a pretty good, I guess. Visualizing the results in PowerView is pretty straightforward. Even if you don't know how to use PowerView, you've got 3 tabs where you can click around from and navigate around your results. Yeah, last but not least, we've got the CSV output. For example, let's say that, okay, PowerView is nice, but let's say you want your results in a custom format, for example, CSV file. We can just click here, open the CSV file with post-processing results. And you can see here, we've got here, for example, the Vswr, the frequency, the S11, the accepted power, reflection coefficient, antenna impedance, reactance, and resistance. So we've got pretty much everything we need regarding the 2D plots here. So you can just take them out, paste them in some Python script to use, for example, matplotlib, plot the measured versus the simulated results. We've done this a couple of times actually, and it's should be quite useful. So you can use this to process your results and analyze your data in any way you want. So and with that, I think I'm finished here, and well, I'd like to thank you all for attending this webinar. I hope to see you all in the next weekly ones, which would likely involve further in-depth geometry modeling, meshing, simulation properties, result visualization, and more, a lot more. Of course, if you've got any questions, feel free to ask. And if there's any topics you'd like to suggest for our next meetings, go ahead and propose freely. So thank you for your attention, and I'm happy to hear your thoughts.
Thank you, Apostolos. Yeah, guys, so if you have any questions at all, any suggestions or things you would like to hear next, please, yeah, just say out loud or write in the chat. We do have some questions in the chat. I think the last 2 we did not answer yet, so I think let's just start with that. So the first one was from Massimiliano about SMA connectors. So do we use models that are given from manufacturers, or is the model derived from the 3D model itself in terms of parameterization, probably?
Okay, if I interpret the question correctly, well, I'm not sure what you mean by the 3D model itself, but essentially the connector has some standards. An SMA connector has some standards. That is the dimension. So the diameter of the outer shell, the ground, the diameter of the inner core conductor, the dielectric material, or the dielectric for sort of dimensions. We have also got the like the pins for the edge connectors. So these are all dimensions that are integrated into the model. So we can just go into the component library, take it out, and just implement it in wherever you want. So yeah, it's a pretty convenient sort of tool that Freecad offers us. And of course, you can create your own components, as I mentioned earlier. Chris asks, is it possible to get polarization information in the results? Not yet, but yeah, this is an interesting question. It is also one of the key features that we're looking to implement, like very easy sort of polarization results. This, for example, may also be useful for determining the axial ratio for circularly polarized antennas, which is of course quite useful, for satellite communications, all sorts of applications. So that's also something that we're looking to implement soon. Indrid asks, I'm not sure if it was discussed yet, but it appears from the Freecad CENOS parameters that users could create their own templates. Is this possible, or will it be possible in the future? I will love future webinars on Freecad CENOS. Yeah, the answer is yeah. Users will be able to create their own templates, and they will just be able to. Okay, this is also. I'll answer the question a bit differently. We're also looking to implement a system for very easily adjusting the parameters of your design. So that means you don't have to go back to Freecad every time you wish to adjust the parameter. Change change how the antenna performs, optimize it for a particular frequency. So this will make your job a lot easier.
Sorry, on this I would like to also comment that actually this kind of is possible already now, because you can parameterize the models that you build on Freecad, and if you parameterize your model, it sort of becomes a template. In what degree, it's completely up to you, or how many different sizes and the geometrical aspects you parameterize, but basically it is already possible.
Yeah, exactly. You can enter as many parameters as you like. There's no limitation in that.
Mm-hmm. And sorry, but I also see that Justin has raised his hand. So Justin, please go ahead. Do you have a question or a comment?
Yeah, thanks very much for that. Have you carried out any experimentation with larger Yagis, such as, or larger antennas, such as those that I'm doing, which is VHF and UHF? One of the issues that I've found is what I started to do with HFSS is to reverse engineer, have a known antenna that's measured, build that within HFSS, then run the simulations, establish the differences, and then adjust the software in order to make it look as close as possible to the built antenna. The problem that I had is the recommended size of the airbox to get an accurate model needed to be much bigger than what was the expected size. And this means that on a typical VHF Yagi of around 144 megahertz, you have around 6 hours processing time. Have you conducted any experiments on time comparisons with other packages in order to see if there's any similarities or betterment in that regard?
That's a very good question. So we have performed not specifically in UHF or VHF, but we have performed like comparisons with other software like CST. We've seen, for example, an aperture coupled antenna, and we've seen that it comes in pretty good agreement, even though CST used FDTD, finite differential time domain solver, while CENOS uses FEM, because these are indeed very important experiments to run in order to verify that, first of all, your solver works, is accurate, and second of all, to make adjustments, as you said, to optimize the solver for the most accurate results. We have not tried it for VHF yet. I guess one of the problems with thin wire antennas, or antennas that don't have a very nice aspect ratio, is, for example, with FEM, meshing becomes a little bit troubling, and it can increase the simulation time quite heavily. But one of the things we're looking for is more antenna designers coming into CENOS, building new antennas that we haven't really experimented with, and then comparing the results that they got, maybe with some measurement. Maybe sometimes even without the measurement, you can tell whether results make sense or not by looking at the E field, by looking at the pattern, the S11. So yeah, comparisons are definitely quite important. And the one last thing, we've also measured, we've also done comparisons with measurements. For example, a user simulated a patch antenna in CENOS, they fabricated it, and the results were quite close. So that's yeah, but yeah, we're definitely looking for more experiments, so we can improve the accuracy even further.
Yeah, I think it's an important factor, especially with frequency, to check the or the comparisons, and also against the real world build antenna. What I found is that with the amount of variances in terms of percentage each time on given frequencies, you can then work out how wideband that antenna needs to be to capture the area where you want it to operate in, with the acceptable build tolerances. For example, at around 400 megahertz, you can have a tolerance plus or minus 1 millimeter with a 5 megahertz bandwidth. It wouldn't be practical necessarily to go to 1/10 of a millimeter if you go to 4 times that at 1.2 gigahertz. So if it's optimized over 20 megahertz, you can use the same kind of tolerances. But of course, it all depends on the accuracy and the variation in the model as well to how that's going to translate in the real world.
Yeah, that's exactly a very valid point. Obviously, depending on your model and your frequency of operation, you're trying to aim for an error that is acceptable for the wavelength, but not too much for destroy your results. But yeah, low frequency antennas are very good candidates to test CENOS against, to look at how, because even if you get the error, like see what the error is, sometimes it's not just about saying, okay, at this frequency always add 5% or minus 5% at some result like S11, but it's also to see where exactly the problem occurs. For example, is the mesh too coarse? Is the solver inaccurate? Are some equations a bit too approximate, for example? So there's a lot of things to look at for sure.
All right, well, thanks for that. Yeah, I think it's for me, the importance is being able to model these Yagis with very low noise characteristics. So anything other than the main desired lobe is very suppressed, if you like. It's a very small ball with the main lobe out. In today's environments, that's so important for there not to be down-facing lobes looking at everything that's producing noise. And of course, as soon as there's a variation to the model, that rear bubble can start to explode, and the low noise characteristics are lost. But I can work with you guys on that, show you some of the results that we've had, and hopefully we can make or work on developing a model that will work and maybe can be used as a template as well.
Yeah, absolutely. We're definitely open to that. I mean, our biggest priority is to produce accurate results for all users, regardless of frequency and design. But yeah, when you say bubble, I assume you mean the lobe, like back lobe and things like that, right? To the radiation pattern.
Yeah, when I talk about the rear bubble, it's when you have if in a Yagi antenna, of course, you've got the main forward lobe where is all the gain. And what I'm referring to as the rear bubble is the back lobes and up and down and side to side. It's everything else other than the main desired lobe.
Yeah, you're absolutely right. I mean, this is very important because front to back ratio is important, of course, to mitigate noise from ground noise, thermal noise, not thermal noise, but interference as well, all sorts of things. So this is definitely an important characteristic of an antenna.
Well, one of the ones that we've been working on and have a repeat requirement for is point-to-point VHF and UHF communications for defense purposes. But of course, they would like to have that rear bubble as tiny as possible, so there's very suppressed output for anybody else to listen to. It's just between those two locations. So if there are side lobes or in every other direction, it's only 12 or 10 dB down on the main lobe, there's still a very high field strength in every other direction.
Yeah, this makes sense. You need to, this is also a part of simulation, you need to adjust all sorts of parameters to see if the main lobe or if side lobes get mitigated, if the back lobe is too strong, if you have grading lobes, for example. In phased array antennas, this is even more common, where you strip the beam and then all of a sudden a small side lobe, but once you adjust the angle a little bit, it becomes a grading lobe. But yeah, this is one of the most important things to look at in simulation results for sure.
Okay, well, I'll share with you what I do at a later stage, but basically I model the antennas in wires only. Then I produce it as it would be a built antenna with the booms, insulators, coax, etc. And then make adjustments to that model in order to replicate the wires only model as close as possible, because of the effects of the real world structure, the supporting structure of the antenna has a negative impact. So there's a percentage correction that has to be added to all of the elements due to the influence of all the materials that are around. Anyway, I won't carry on that subject. I'm sure there's other questions as well, but thanks for your answer.
No worries. Thanks a lot for bringing an important topic up.
Thank you, Justin, indeed. Does anyone else has anything to ask or to comment or any topic they'd like to discuss with us at this point? All right, then I'll take it as a no. So, okay, then in that case, thank you all again for coming. It was nice to see so many of you. And yes, if you have any specific topics you'd like to for us to cover in the next webinars, you can definitely reach out to us also separately and after the webinar. If there is anything, for example, in Freecad that you'd like for us to elaborate. And besides that, then yes, again, thanks for joining and see you in the next webinars.